Hi guys, welcome to your lecture. I hope you're having a very good public holiday. And so this is your lecture on Factorial ANOVA. Please make sure that you have listened to this before you come to class the following week. Okay, let's go ahead and get started. Now we have another Stats Matters activity. This is your last one. So this is called Reporting for Duty. So I want you guys to think about how statistics is relevant not just for your life now, but how you can be using statistics in the future as well. One of the things I want you guys to get out of this class is that the skills you're learning are not just for passing this class, and they're not just for passing your other classes now. You in the diaries that you guys might have done, you might have seen that you're using, in fact, statistics and research methodology all throughout your life. And the careers you guys have will also end up using some forms of statistics and research methods. So for this activity, I want you guys to think about what you want to do after you leave NUS. What do you want to be when you grow up? So think about the job you want to have after you graduate from NUS. Now, I want you to think about the actual job title or role, not just I want to be in in industry. I want to be in fashion. I want to be in baking. No. Tell me exactly what is the role that you want to have. I want to be a clinical psychologist. I want to be a social worker. I want to be a professor, whatever it might be. Think about the specific role. And this can be either, entry-level role that is realistic, or it could be an aspirational role that you want to have eventually. Either works. So write out what tasks someone in this profession does and how they might incorporate statistical skills in their work. And then I want you to have a conversation with ChatGPT. And just use this prompt here. You are a maybe clinical psychologist or whatever it might be. I'm going to interview you about your job to learn about how it relates to what I'm studying. Do you understand? And then you can use the prompts that I provided in the worksheet that are in Canvas to help guide the conversation. And you're going to interview ChatGPT in the role of the profession that you want to be when you grow up. So after you finish having this conversation, I want you to reflect on the conversation, write a reflection summary or paragraph about what you learned, and why taking a course in research methods and statistics is relevant for the job that you want. And then you can submit this, of course, as always, along with a copy of your conversation for 1 bonus point on the final exam. Okay, so going on to the main part of today's lecture, we have, today we're talking about Factorial ANOVA. So we'll talk about main effects and interactions. We'll talk about what it means to partition variance. We'll just kind of review that from the previous lectures. And then we'll talk about how we can partition variance in the Factorial ANOVA. And then we'll end by going through Factorial ANOVA in SPSS and how to write up the results. Okay, so for our lecture today, the example comes from an article by Glick et al. And this is a study that evaluated the effect of how women dress, whether they dress sexy or neutral, on perceptions of perceived competence if that woman is employed in a high status job, such as a manager, or a low status job, such as an assistant. So just like before, I had ChatGPT recreate the actual data, but I did this using the sample size and means of standard deviations and results that were reported in the article. So the data itself has been, it is recreated from ChatGPT. However, the results are exactly what they report in the article here. Okay, so this graph represents the results from the article. Normally, I'd ask you guys to describe this using Blue Class, but because today is a pre-recorded lecture, I'm going to ask you guys to please write your descriptions in Canvas. So go on to pause the video, go on to Canvas, and try to describe this graph and what this is telling us about perceived competence for women when they are managers or assistants and when they're just sexy or neutral. Okay, so today we are talking about factorial ANOVAs. Now, factorial means more than one factor. So in the past couple of weeks, we've been talking about a one-way between subjects ANOVA. One-way meaning we have one independent variable. You guys recall that we were talking about the effect of the curse word on the persuasiveness of a message. There is only one IV, which was the curse word, and whether it appeared at the beginning, end, or not at all within the sentence. In today's example, we have two IVs. We have one IV called appearance, which is 2 levels, sexy and neutral, and we have a second IV, which is job, and that is manager and assistant. Now, this is a between subjects design, which means that participants contribute only one data point, and they only experience one condition. So different people are going to be seeing the different conditions. So maybe you're in the sexy manager condition, or you're in the neutral manager, or you're in the sexy assistant or the neutral assistant. So you, as a participant, you only see one of these conditions. This is a between subjects design. We call this type of design a 2x2 design. The 2 refers to the number of levels within that IV. So for appearance, there are 2 levels, sexy versus neutral, and job, there are 2 levels, manager versus assistant. Maybe we have a third level. So maybe we have what's called a 2x3 design, where job has 3 levels, manager, assistant, and CEO. This is a 2x3 design. Those numbers refer to the number of levels, and so the fact that we have a 2x3 tells us we have only 2 IVs in this design. Or maybe we have a 2x2x2 design, where we have 3 IVs, and each IV has 2 levels. So maybe we have appearance, again, sexy, neutral, job, manager, assistant, and maybe we're looking at sex, so it's either males or females. So you can see how we use this nomenclature of 2x2, 2x3, right, to help portray what this design is. Okay, so let's come back to our original 2x2 example. So, factorial ANOVAs means that there is more than one IV. We want to know what is the effect of each factor alone, as well as the effect of the factors together. So in other words, we are interested in the main effect of each factor and the interaction between the IVs. Now, main effect means that we look at the effect of one variable while collapsing across all other IVs. So in this example, we can look at the main effect of appearance. And to do this, we're going to ignore the job grouping factor and just look at the mean competence ratings for people who are in the sexy condition versus people in the neutral condition. So a main effect means that we collapse or ignore the other variables, and we look at just the effect of that one variable. We can also look at the main effect for job. So again, we're going to collapse across the appearance variable. We're going to ignore this. We're going to look at just the average of people in the manager condition and compare this to people in the assistant condition. So these are main effects. Again, main effects means that we collapse or ignore the other IVs to look at just that one IV. When we do factorial ANOVAs, we do want to look at main effects. We want to see what is the effect of each IV by itself. But importantly, we're usually really interested in the interaction effect. Normally, the reason we include multiple IVs in a design is because we're interested in how those IVs interact together. If we don't expect them to interact, then normally it's better to not look at them with these variables in the same design because that reduces your power. So usually we are interested in how one IV influences the effect of another IV. An interaction means that the effect of one variable on the DV, so in this case, maybe we have the effect of being a manager or assistant, and how this affects perceived competence as a function of whether that person is just sexy or neutral. Now, I've got 2 graphs to display the results. Sometimes it's easier to think about this in bar charts, and it's easier to visualize and think about this in terms of line graphs. So I put them both up here. But basically what we want to see is that the effect of, and again, we can switch this around and talk about now as sexy versus neutral. So whether you dress sexy or neutral, how does this affect perceived competence maybe changes as a function of whether the person is a manager or assistant. So the interaction effect means that the effect of one variable, in this case the appearance, on your dependent variable changes based on the level of another IB. In other words, based on whether the person is a manager or an assistant. And we can see that this does seem to have an interaction where if you're an assistant, it doesn't look like it matters that much whether you're dressed in a neutral or sexy manner. You can see that the two bars at the top, the gray bars are roughly the same, or if you look at the line graph on the right, those are roughly the same. So it doesn't really matter for the assistant how they're dressed, but it does seem to matter for the manager. And you can see this very clearly in that line graph at the bottom, where dressing neutrally seems to result in higher levels of perceived competence compared to dressing sexy. So dressing sexy reduces the perceived competence, at least appears to, based on this graph, it reduces the perceived competence for women who are managers, but not for women who are assistants. But this does not affect perceived competence, it does not affect perceived competence for assistants. So whether you're just neutrally or sexy does not affect your perceived competence if you're an assistant, but it does affect your perceived competence if you're a manager. That's what this is telling us. So here we're looking at an interaction. Again, an interaction means that the effect of one IB on your dependent variable changes as a function of the level of another IB. And this might sound a little bit familiar because, in fact, this is the same idea as moderation that we talked about a few weeks ago. Here, we saw that the effect of our studied on grades changes based on whether you have high interest or low interest. So if you have low interest, studying more leads to better grades. But if you have a high interest in the topic, then increasing the amount of time you spend studying doesn't seem to affect your grades because you always have high grades. So this is an interaction effect. So moderation is actually just another word for interaction. The effect of one IB, in this case the hour studied, on the dependent variable of grades changes as a function of whether you are high or low interest. Okay, so quiz yourself. Which of the following describes an interaction effect? I'll give you a couple of seconds to answer before I show, or to think about this before I show the answer. Okay, the correct answer here is B. Caffeine boosts working memory accuracy when people are sleep deprived, but it has little to no effect when people are well rested. So here, the effect of caffeine on memory changes as a function of whether you are sleep deprived or well rested. Now, the top 60 minutes of studying yields higher recall than 30 minutes, and using practice tests beat simple rereading. This describes two main effects. So there's a main effect of the amount of time you spend studying, so 60 minutes results in better recall than 30 minutes. That's one main effect. Practice tests results in better recall than rereading. That's the second main effect. So these are two main effects, but there's no interaction being described here. It's not like one of these variables on recall changes as a function of the others. It's just two main effects. Similar for C, participants respond slower in moderate noise than in quiet environments. That's one main effect. And people are faster in the morning than in the afternoon. That's another main effect. So these are just two main effects. And then the last one, a 5-minute mindfulness break and exposure to nature images have no effect on cortisol or self-reported stress. This is just actually no main effects, no interactions at all. So the correct answer here is B. All right, second, quiz yourself. Pause the video and try to draw this effect. So with background music, extroverts solve more problems than introverts, but in silence, introverts outperform extroverts. All right, here's the answer here. So we can see that when there's background music, extroverts have a higher performance than introverts, but in silence, this flips. So this is what we call a crossover interaction, where the lines you can literally see are literally crossing over each other. So in one condition, extroverts outperform introverts, but in the other condition, introverts outperform extroverts. The effect of being an introvert or extrovert on performance changes as a function of the environment, whether there is music or no music. Here's the second one. Draw this effect. So younger adults recall more words than older adults, and providing category cues similarly improves recall in both populations compared to no cues. So pause the video and try drawing this effect. Okay, so here is the result, the answer. So we see younger adults recall more words than older adults. So younger adults mean the darker bars here. There is a main effect such that we have more words being recalled by younger relative to the gray bars than older. Category cues provide more recall than uncued. So we have higher bars on the cued condition compared to the uncued condition. So what we have here are two main effects, but no obvious interaction effect. What I mean is that the effect of cued or uncued categories on word recall doesn't seem to change as a function of younger or older adults. What we always see is that cued results always in more recall than uncued. Younger adults have more recall than older adults. So we have two main effects, no interaction effect here. Okay, last one, draw this effect. For mild depression, CBT and supportive counseling yield similar therapeutic gains, but for severe depression, CBT outperforms supportive counseling by a wide margin. Pause the video and try to draw this. Okay, so here is the answer. So we see that for mild depression, they're roughly the same, but when the depression is severe, we see a big improvement in CBT relative to therapeutic or supportive counseling. So this is an interaction. So we see that the effect of CBT, those lines are not parallel. And that's kind of what we're looking for, is if the lines are not parallel, then it suggests that there's an interaction effect, right? The effect of CBT and supportive counseling have similar effects for mild depression, but there's a very different effect for severe depression. So again, the effect of one IV, in this case the type of therapy, on therapeutic gains differs as a function of another IV. So it differs as a function of whether depression is severe or mild. So yeah, one trick to kind of quickly figure out, is there an interaction or not, is to look at whether the lines are parallel. If the lines are parallel, it suggests, of course we need statistics to back this up and confirm it, but it suggests main effects, but no interaction. When the lines are not parallel, like here, then it would suggest that we have an interaction effect. But again, of course, we always have to confirm this using statistics, and so that's what we're going to talk about now. Okay, so the independent factorial designs have more than two IVs, and each IV is between subjects. Main effects describe the effect of each IV while collapsing across the other IVs, and interactions describe the effect of one IV at each level of another IV. Okay, guys, so let's get started. Start with big picture here. The ANOVA is an analysis of variance. What I mean is that we are partitioning variance into that which we can explain using our model and that which we cannot explain, because there's variance due to other stuff like individual differences or compounds or just extraneous variables that we have not control for. The ANOVA, whether we're talking about ANOVA for factorial ANOVA or the ANOVA for the one-way ANOVA or the ANOVA that we use in regression model, it's just a analysis that will partition the variance to assess how much variance can we explain with our model, how much variance can we not explain with our model. The ANOVA is a ratio, right? You guys know this. It's a ratio of the mean squares model over mean squares residual. And of course, those mean squares are based on the sums of squares. Now, the sums of squares model always means the difference in what we predict using our model versus what we would predict using the grand mean, or the mean of y. So it's a difference between what we predict based on the means of the groups, or based on that correlation, depending on if you're using a linear regression with continuous IVs, or the means if you're using a categorical IV, and what you predict from just using the mean of y. The residual is the difference between what we observe, so the actual data that we observe, and what we would predict using our model. So this is your error. This is the prediction error. So the ANOVA is an analysis that will partition the variance into variance explained on top and variance not explained on the bottom. So if you recall, when we did the linear regression, sums of squares model is the explained error, sums of squares residual is your unexplained error, and then we of course have the total. So we have a total amount of variance. You see there's a lot of variance in this data. If you look at those dots, there's quite a bit of variance. Some of the variance we can explain thanks to the correlation between our studied and test performance. So because these are correlated, we can explain why people who study more tend to have higher grades and why people who study less tend to have lower grades. So that's the difference between what we predict with our model and what we would predict using the grand mean. We don't predict everybody's going to get the exact same score like the grand mean does. No, we predict some variance based on how much time you spend studying. But there's some unexplained variance, right? Not everybody falls on that diagonal line. So that's due to things we can't explain. We can't explain why somebody who studies 2 hours, some people get a 19, and other people get a 38, and other people get like a 70 something there. We can't explain that variance. We can explain why overall people who study more get higher grades than people who study less, but we can't explain the variance that occurs within each of our study condition. That's due to other stuff we're not including in our model. So that's our prediction error. So this is the sums of squares residual and the sums of squares model. So the variance we can explain with our model compared to the variance we cannot explain. This is the residual error. We did the same thing when we had a categorical variable with 2 levels. So here we were looking at the difference in grades as a function of whether you're a psychology major or not a psychology major. And we determined that there is a difference between the grades overall. The grade for psychology majors was on average higher than the grade for non-psychology majors. And so we wouldn't expect everybody to have the exact same grade. We would expect grades for psychology majors to be higher than grades for non-psychology majors. So this is the error or the variance we can explain. There is some variance in the data that is systematic to group assignments. This is, again, your SS model. The difference between the means of our groups, so that's the model, and the grand mean. The residual, just like what we saw before, is the unexplained error. It is the difference between what we predict with our model and what we actually observe. So just like with the linear regression, sums of squared model is the difference between what we predict with our model and the grand mean. The residual is the difference between what we observe and what we would predict with our model. Again, same thing that we saw with a one-way between subjects and ANOVA, but now we just have 3 groups. So we have here the groups control, beginning, and end, and we have some variance and the persuasiveness ratings. So there's a lot of variability in the data, and we can see that some of this variability or some of this variance in the data can be explained because the variance is systematic to group assignment. People in the control group have lower persuasiveness scores than people in group beginning. So there's some variance that we can explain using the group means, using group assignment. That is systematic variance. And this is the difference between what we predict using the group means relative to the grand mean. And again, we have some unsystematic variance in the data, the sum of squares residual, which is the difference between what we observe and what we predict using the model. The variance that is systematic to group assignment is your sum of squares model. Variance that is unsystematic and is within groups, that's your sum of squares residual. And this is the same in the linear regression, in the t-test, and in the one-way ANOVA. It's all the same idea of partitioning variance into variance we can explain with our model and variance that is unexplained. Okay, so again, this is going to be a bit repetitive, but the ANOVA partitions variance into model variance and residual variance. So the ANOVA has two main sources of variance, the sum of squares model, which is the difference between the predicted value based on the model minus the predicted value based on the grand mean. And of course, that's squared error. And then the sum of squares residual, which is the difference between what we observe and what we would predict using the group mean. And again, that's of course squared. And this is the same for all the different kinds of ANOVAs we've just discussed. This is going to result in an F ratio. So you know that the ANOVA is an F ratio. That is the mean squares model over the mean squares residual. And of course, the mean squared is calculated using those sums of squares. So ultimately, the F ratio is a ratio of systematic variance between groups that we can explain relative to unsystematic variance we cannot explain. This is the same pattern we've been seeing over and over again. Okay, so now we're going to apply the same concept to a factorial ANOVA. We see that there is variance in the data, right? The means are not all the same, so inherently that means there is some variance in the data. Some of this variance is going to be explained by our model. Some of this variance is unexplained by our model. But we can further partition the variance explained into the variance explained by factor 1, so main effect 1, variance explained by main effect 2, or by factor 2, and variance explained by the interaction effect. So each of these different effects, the two different main effects and the interaction, can each explain a unique amount of variance. And together, these account for the variance explained by the full model. So when we talk about a factorial ANOVA, we're going to still look at variance explained relative to variance unexplained, but we're going to further break down variance explained into the variance explained by each main effect and each interaction. And so what we actually have are three different F ratios. So mean squares model can be broken down into the mean squares for appearance, the variance explained by the job, and the variance explained by the interaction effect. Okay, ANOVA partitions variance into two main buckets. Variance explained using the model and variance unexplained, which is your residual error. And the variance explained by the model, which is your sum of squares model, is equal to the sum of the square difference between the predicted value of y based on your model and the value predicted using the grand mean. The variance unexplained by the model, which is your sum of squares residual, is equal to the sum of the square difference between each observed data point and the value that would be predicted using your model. In factorial ANOVA, we're going to further partition the variance explained by the model into the variance explained by each main effect and the variance explained by the interaction effect. And you're going to calculate an F ratio for each source of explained variance. Okay, so let's move on. So we've got a total amount of variance that can be broken down into the variance that is unexplained, your residual variance, and the variance that is explained, which is your model variance. And then, again, we're going to break down the model variance into the different sources. So the sums of squares appearance, so for factor 1, the variance explained for job, and the variance explained by the interaction between appearance and job. And again, we're going to essentially be calculating 3 different F ratios to assess the whether the variance explained by each of these main effects and interaction is reliable. Okay, so let's do this. Let's break it down. We're going to start with the total sums of squares, so the model. So we're going to look at everything together. This is the total amount of squared error between the model, which is the group means, and the grand mean, weighted by sample size. We're going to calculate this exactly the same way we did for the previous ANOVA. So if you recall, the one-way ANOVA, the sums of squares model is equal to the difference between each group mean and the grand mean, quantity squared. It's exactly the same for the factorial ANOVA. We're going to take the difference between each group mean minus the grand mean, and we're going to square each of those different scores. So we're looking at the difference between each mean and the grand mean. Now, guys, I'm not going to ask you guys to calculate anything on the exam. You know this already. But I think it's sometimes going to be helpful to go through the calculation because that might be help make this concept clearer. So don't freak out about the numbers. Just follow along because I think sometimes this might just help explain what the sums of squares model is. So this is the difference between each group mean and the grand mean. So this is the difference between the mean for neutral system, which is 5.18, minus the grand mean, which is 4.88 quantity squared, plus the difference between 5.42 minus 4.88 quantity squared. And of course, each of these are multiplied by the sample size n. Plus, in this case, sexy assistant, 4.85 minus 4.88 multiplied by 25. That difference is squared. Plus, and then again, sample size 14 times mean of sexy manager, which is 4.13, minus the grand mean, 4.88 quantity squared. So when we're talking about the sums of squares model, we're going to calculate this in the exact same way we did for the one-way ANOVA and for the t-test and even for the linear regression model. It's just the difference between what we predict using our model, which in this case is the group means, minus the grand mean. And the degrees of freedom is calculated also exactly the same as we saw before. It's just k minus 1, k meaning the number of groups we have. So we've got 3 degrees of freedom here. Now we're going to do the exact same thing for each of the main effects. So we're going to now look at how to calculate the sums of squares model for appearance and the sums of squares for job. And again, we're going to do the exact same thing we did. It's just the difference between what we predict using our model, which is the means for each of these main effects, minus the grand mean. So here, we've got 27 people who were in the neutral condition, and the average perceived competence for people in the neutral condition, collapsing across whether they are assistants or managers. We're ignoring that. The average perceived competence for people who were dressed neutrally is 5.30. We're going to minus the grand mean, again, 4.88 quantity squared. Plus, we've got 39 people in the sexy condition. The average for people dressed in sexy conditions, the average perceived competence is 4.59 minus, again, the grand mean, quantity squared. So it's the exact same concept. is the sum of squares appearance is equal to the difference between what we predict with our model and what we predict using the grand mean. And so again, we could do the exact same thing here for job. So it's the difference between what we predict using the model, the means for assistant and manager, and what we predict using the grand mean. And again, when we're doing this for main effects, we are collapsing or ignoring the other variables. So we're looking just at the perceived competence for people who are in the assistant condition. And we are ignoring the fact that some of these people are maybe just in a sexy condition, or sexy, or some of them are just neutrally. We're ignoring that for now, and we're just looking at perceived competence of people who are assistants and people who are managers, or actually women, because this is all looking at perceived competence of women. Okay, so for the main effects, pretty easy. So sum of squares model as a whole and sum of squares for the main effects is just the difference between each group mean and the grand mean, multiplied by the group size, and then of course squaring the different scores. Now let's look at the interaction. So we're going to look at the variance that we can explain using the interaction between appearance and job, because of course this can explain a little bit more unique variance. Now, if we want to calculate it, honestly, the easiest way to calculate it is just to take the sum of squares model minus the sum of squares appearance minus the sum of squares job. And you do the same thing for the degrees of freedom. Again, I'm not actually going to ask you guys to, pull out a calculator and do this on the test. So you don't really need to do this. I am more interested in how you guys can understand what the interaction effect means. So let's look at the more intuitive understanding of what is an interaction effect. So an interaction effect of appearance by jobs is you can think of this as the difference between differences. It's the difference in perceived competence being a manager and an assistant when your appearance is neutral compared to when it is sexy. Or put another way, it is a difference in perceived competence at your job as a function of how you are dressed. So what we can see is that when you are an assistant, it doesn't really matter, right, whether you are dressed sexy or neutral. The difference between being a neutral assistant and a sexy assistant is very small. But when you're a manager, your appearance does have a big effect, right? Here, dressing sexy greatly reduces your perceived competence if you're a manager, compared to if you are just neutral. This is what the interaction effect is looking at, is the difference in being a manager and assistant as a function of whether you are just sexy or neutral. And so this is how we would put it in the regression equation, right? So the main effects are exactly what you've seen before, right? So the main effects are just the difference between the means. So if we have neutral and assistant as our reference conditions, this is the 0, 0 condition. The B1 appearance, this is simply the difference between being a sexy assistant, so B1 being for the appearance. So if neutral is the reference, then sexy is 1, minus a neutral assistant. And B2 is the difference between being a neutral manager minus a neutral assistant. So you guys remember when we talked about linear regression that the coefficients is simply the difference between the means of these two groups. The interaction is the difference between differences. So it's the difference between being a neutral assistant relative to a sexy assistant, and the difference between a sexy manager and a neutral manager. All right, the sum of squares residual is exactly what we have talked about before. Just we call it the sum of squares residual is the difference between each observed data point and what we predict using our model, which is the group mean. So it's the difference between what we observe and what we predict. So it's hard to show, what I'm showing you is an example from the one-way ANOVA. It's a bit hard to show you a 3D scatter plot, so you have to use your imagination. But it's the same exact idea. If you want to calculate it, it's a formula, but again, we're not actually going to be calculating things on the exam. Just understand the concept that sum of squares residual is the difference between what we observe and what we would predict with our model. And here, degrees of freedom is equal to n minus k, where again, k is the number of groups that you have. Okay, so in-term summary, calculate the variance explained by the full model and the main effects in the same way as you did for the one-way ANOVA, which is the sum of the squared error between the group mean and the grand mean multiplied by n of each group. Now, the linear regression equation includes a term for the interaction, which describes the difference between differences. In other words, it refers to the differences between factor 1 groups at various levels of factor 2. And then, just like what you saw before, the coefficients for the main effects refer to the differences between group means. Okay, so let's go through how to do this in SPSS. Now, let's just quickly review the design. So we have 2 IVs. Each IV has 2 levels. This is how my data is set up in SPSS. And this is how it's coded. So neutral and assistant are my reference categories. 1 and manager are my are coded as 1. So I go to univariate, and I put in competence or perceived competence as my dependent variable, and appearance and job can both go into fixed factors. You can ask for contrast. I'm just going to get simple contrast using the first category as my reference category. So using neutral and assistant as my reference category. So that here, it's just going to compare each of these. So appearance versus, neutral versus sexy, and it's going to compare assistant versus manager. And again, first being whichever one was coded as 0. We can get some plots here, so we can ask for a means plot using, it's always nice to have a plot of the interaction. You could also get plots for your main effects if you want as well. That's always good. We don't really need post hocs for this design because there are only 2 levels of each of our IVs. If we get a significant main effect for appearance or a significant main effect for job, this automatically means that there's a difference between those 2 levels because there's no other there's no other group who could differ. So a significant effect for appearance means that sexy is different from neutral. Those are the only 2 groups that can possibly differ. So we're not going to bother with the post hocs for this particular design. And in fact, if you put them in, if you ask for post hocs, you're just going to get a bunch of errors saying it can't run the post hocs because there's only 2 levels. Okay, you should also ask for EM means, which means estimated marginal means. These estimated marginal means provide a more fair comparison of the group means by taking into consideration any covariates or unequal group sizes. I like them because then you can also do pairwise comparisons, which is just basically another way of doing post hoc tests. So I always ask for estimated marginal means. Do this for all of your main effects and the interaction. Compare the main effects, get the simple main effects, and then you can ask for an adjustment. Here we'll just do the SIDAC. So again, never use LSD, right? So you guys have already learned that the least square difference is just basically means there's no adjustment at all for multiple comparisons. We do want to correct for the multiple comparisons that are being done. So choose either Bonferroni or SIDAC. I have no reason for choosing SIDAC over Bonferroni other than I'm just using this as an example here. Okay, and then finally, get your descriptive statistics, effect size, homogeneity test, residual plus, and the parameter estimates. And if you want to do parameter estimates, you can also do those using robust standard errors if you want to do any kind of bootstrapping. which you can do here. Not required, but if you want to do bootstrapping, maybe you're concerned about violating some assumptions, you can do that here. Okay, so these are the results. So we see sexy and assistant are both coded as 0. Neutral and assistant are both coded as 0. Sexy and manager are coded as 1. These are the mean, standard deviations, and ends for each of our groups here. And these are the bootstrap confidence intervals. Okay, so not much to see here so far. Let's check the test for homogeneity. Just like what we saw before, Levine's test is testing the null hypothesis that the error variance is equal across the groups, which is what we want it to be. So we want this to be not significant. That is not significant, so that's good. So we satisfied this assumption here. I always like to scroll down to the plot first. I mean, you don't have to, you can just kind of go in order, but I think it's always really helpful to scroll down and just look at the plot to see, what's going on. Because this can usually, pictures can tell you a lot more and a lot faster than words can sometimes. And so it's just nice to scroll down and see, does it look like there are any main effects or interactions? To me, this looks like an interaction effect because I can see that there's a very big effect of sexy and neutral when you're a manager, but it doesn't seem to have much of an effect when you're an assistant. So it gives me an idea for what I should be looking for when I'm looking through the actual results. Okay, so this is the results here. So this is your ANOVA table. Now, the corrected model is the full model, which includes your main effects and the interaction. So this is that full model. And so here this is the variance we can explain. Sums of squares is 13.149. There are 3 degrees of freedom. Then this is k minus 1. This results in a mean squared of 4.383. Again, this is simply the sum of squares divided by the degrees of freedom, which gives you a mean squared. And an F, which is the mean squares model over the mean squares error. So 4.383 divided by, we scroll down, the error is 0.742. And this gives us an F of 5.909. Significance value, if we keep going across the top line, is 0.001. This is less than 0.05, which means this is statistically significant. So the model as a whole, this is your omnibus model, does explain a reliable amount of variance. In other words, there is a significant amount of variance that is systematic to group assignment. And partial A squared is your effect size, 0.222. Okay, great. So this tells us that as a whole, yeah, we have some variance that is systematic. Now we want to break this down more. Intercept is the model when all IVs are at their reference level. So this is essentially your NP model. We don't usually use this. This is your reference group. So this is basically what you predict using that reference group, neutral, assistant only. But yeah, we don't normally use this. Move on to main effects. So this is the variance explained just by the main effect of appearance, so that the IV of appearance. So this has sum of squares 10.102, 1 degree of freedom. This has an F of 13.620. So again, it's that 10.102 divided by 0.742, which is the error. And this is significant. So this tells us that the variance that is systematic to the appearance, so whether somebody is sexy or neutral, is reliable, that is significant. And because we only have 2 levels, we already know that this means that sexy is significantly different from neutral. If we had more than 2 levels, like we did in the previous week when we talked about one-way ANOVA, we wouldn't be able to determine from yet which group differs from which. But here we only have 2 groups. So now we move on to job, and we can see that there is not a significant main effect of job. The variance that is explained by job is not reliable. So there's not a significant or a reliable amount of variance that is systematic to job assignment. So this tells us that manager is not significantly different from assistant. All right, but what about the interaction? Because that's really what's most important here. Does the variance explained by appearance differ as a function of the job you're in? And here we see that, yes, there is a significant interaction effect, as it's 4.783 with p-value of less than 0.05. So this tells us that there is some variance that is systematic to assignment that also differs as a variance that due to appearance that differs as a function of somebody's job. Okay, so that's interesting. We have an interaction effect that we will want to explore more. This is your residual error. This is the variance that we cannot explain, that is unsystematic due to other stuff. So again, this is the difference between each observed data point and what we predict using our model. This is your total amount of variation in Y that includes the intercepts, plus the individual factors and interaction error. And again, this is one that we usually just ignore. It's used for descriptive purposes, but usually we ignore this one. This is what we're more interested in. This is the total variation in Y, excluding the intercept, but still including the individual factors, interaction, and error. Okay, these are those estimated marginal means. And again, these are adjusted means that account for covariance and unbalanced data. In other words, unequal group sizes. And they tend to provide a more fair comparison of group means when the design is very unbalanced or if it includes covariance. And it does this by averaging across factor levels as if the groups were equally sized. So you can see they're usually very similar to what you would get in the descriptive statistics. So the estimated marginal mean for the grand mean is 4.895, and descriptive that doesn't do any kind of correction is 4.8832. So they're very similar, but the estimated marginal means are just a little bit adjusted for those covariance and unequal group sizes. And it's going to give this to you for all of the main effects and interactions. So here, again, the descriptive statistics, not taking into account group sizes, the average for neutral is 5.3044 there on the right, and the average perceived competence for sexy is 4.5915. But the estimated marginal means on the left, which are adjusted for group sizes, for unequal group sizes, you can see are slightly different. Okay. Now, the reason I really like the estimated marginal means is because we can look at the pairwise comparison, which is comparing each of the levels of your main effects. So here, neutral versus sexy. So neutral minus sexy, there's a difference between the means of 0.810, and it's conducting essentially a t-test, because this is the difference over standard error. You guys know that's a t-test. And this is significant. And so you can see on the right that there is a significant difference between perceived competence when somebody is just sexy versus when they are just neutral. And you can look down further and look at the univariate test. This is a test of whether this difference is reliable. And it's because, again, we only have two levels of our IV, the univariate test is going to match exactly what this pairwise comparison says here. All right, and then we can see the same thing for the main effective job. So we have on the top the estimated marginal means of 5.015 and 4.775, and then we've got the pairwise comparisons. So these are the perceived competence for assistants minus the perceived competence for managers. Is the difference is 0.240, and this difference is not significant. So you can see the significance value is 0.278. That is above 0.05. This tells us that there is not a significant difference between the perceived competence of managers and assistants. And again, if you look down at the bottom, you can see the univariate test. That is not a significant ANOVA. So this contrast is not reliable. So again, this means that the variance that is related to manager and assistant is not systematic. All right, and now we have the interaction. So appearance by job. So here are the estimated marginal means for each of our 4 groups here. And look at the pairwise comparisons. So these are basically post hocs that are based on the estimated marginal means. So we can compare. Let's just look at the first line. We're going to look at the assistants, and we're going to look at neutral versus sexy. So when you're an assistant, is there a difference when you are just neutral versus when you're just sexy? And the difference is equal to 0.330. That is not significant. Now let's look at a manager who is just neutral versus sexy. This yields a difference of 1.290, and this difference is significant. So we can see that we have a significant interaction, and it's because just being neutral, the appearance of a person does not impact perceived competence if you're an assistant, but it does affect perceived competence if you are a manager. This is what the interaction term is telling us. All right, now SPSS is going to give it to you in both ways. So previously it was job by appearance, now it's appearance by job. Again, sometimes it makes more sense to look at it in one way versus the other. So we can again look down at neutral. So now we're looking at just people who are just neutral. Is there a difference between managers and assistants? That difference is 0.240. That is not significant. If you're just sexy, is there a difference between managers and assistants? That difference is significant. So which way you want to interpret this, whether you want to use the appearance by job or job by appearance, just depends on how, like what your hypothesis is, and like how you want to frame this. But it's giving you the exact same results here. Okay, what about those custom contrasts? Let's find contrasts here. So I asked for a simple contrast. No, I did ask for it to be the first one to be used as reference group. For some reason, SPSS is using the group neutral as the reference. So it is category 1. So it's a little bit confusing because it's category equals 1, but this means the first level is being used as the reference. So as neutral and assistant are the reference here. And what we see is that for contrast 1, which is the, let's see here, this is for appearance. So contrast 1 is appearance. There is a significant difference here. So sexy relative to neutral does have a significant difference in perceived competence. So the contrast is equal to minus 0.810, and that difference is significant. And that overall model is significant, you can see from the test results. And for contrast 2, which is for job, we can see that this is not significant. Okay, so here the contrast is minus 0.240, and this is not a significant effect. And again, this is you kind of probably didn't need to do this because you already got this from the pairwise comparisons. This is really just redundant to what you've already learned. Okay, and then here are the effect sizes. Now, partial eta squared is the proportion of unique variance explained by that variable that is not explained by other variables in the analysis. And so you can kind of get a sense for which variable has the largest effect here. And then the test point talks about omega squared. I actually don't see this reported quite as often, but sometimes if you see an omega squared, just know that this is just another effect size, and it's effect size for the population. All right, lastly, we did ask the parameter estimate. So this is just giving us those coefficients that we can put into our regression equation. So, oddly, it used sexy and manager as the reference categories. You can see this because it has zeros for this betas on the left. I'm not sure why it did that, but it's using those as the reference categories, but that's okay. So if we put this into our regression equation, B0 is the reference category. So that would be sexy manager, because that's the one that gets zeros. And then the second one will be B1 for appearance, which is the difference in between the means. So it's neutral manager minus sexy manager. B2 is for job. So this is, again, the difference between the means. So it is assistant minus manager. And then we have the interaction term. So we're going to use these coefficients, and we can fill this in to our regression equation. And that's all. So this just tells you that for every 1 unit increase in appearance, we're going from a sexy to neutral, there is an increase in perceived competence of 1.290. For going from a manager to an assistant, there is an increase in perceived competence of 0.720. And the interaction effect tells us that there is a difference in the perceived competence for managers and assistants, and this perceived competence differs as a function of whether you're just neutral or sexy. And then, okay, here the bootstrap parameter estimates for those parameters. Okay, so XPace's output shows an F ratio for the full model, for each main effect, and for each interaction. And each F ratio represents the variance explained by that source and the variance unexplained. The estimated marginal means provide a fairer comparison by adjusting for covariance and unequal sample sizes. Pairwise comparisons are like post-hoc comparisons that use the estimated marginal means, and the parameter estimates provide the beta coefficients for the regression equation. Now, guys, again, if that was a lot, I just want you guys to remember, you need to understand the concepts. You need to understand conceptually what are these things doing and how to apply them. You don't need to actually do the calculations for your final exam. Okay, now when do you use the factorial ANOVA? When you have one continuous dependent variable, 2 or more categorical IVs. Now this is a, what I just showed you was for a fully between subjects design. In a couple of weeks, we will talk about what happens when one of those variables is within subjects. But for now, we're just talking about between subject designs. And of course, just like before, you should be meeting all of the other basic assumptions for parametric analyses. What happens if you don't meet those assumptions? Well, you can remove outliers or transform the data. Now, unlike the one-way ANOVA, there's not really a good non-parametric equivalent for a factorial ANOVA. So you can just maybe make your alpha criterion more conservative by maybe going from 0.05 to 0.01. That's maybe something you could do. But there's unfortunately not a great way of doing a non-parametric version of this, at least not one that's kind of simple. To write up your results, for each main effect and interaction, indicate the statistic, degrees of freedom, p-value, effect size, and any kind of plan contrast or pairwise comparisons or post hocs that you did. Usually graphs and tables are helpful. Always include this in your write-up. So, you know, what's the research question? What's your hypothesis? What's your IV? What's your DV? What test did you conduct? You know, what's the sample size? Did you have any violations? What are the results? Now, importantly, just like I said before, when you talk about results, don't just say this is significant or not significant. Make sure you describe the data. You know, you indicate this means that, you know, group sexy has lower perceived competence than group neutral, right? So really make sure that you're talking about what the results mean and bringing it back to the IVs. Don't just say that this result is significant. Tell me significant how. Which group is higher or lower, better or worse, you know, faster or slower than the others. So make sure that you relate the results back to the hypothesis, and do you reject or fail to reject your null hypothesis? All right, so this is an example. Again, you don't need to copy, and I would recommend not copying exactly what I say, but this is just an example for how you can write up a result section for this for this kind of results. You guys can pause this if you need more time, but I'll move on. And then you might include, again, like I said, a table of the descriptive statistics and a figure. These are always really helpful. Your book has a nice flow chart for how to go through a factorial ANOVA. So just kind of following through this, that's quite useful. Okay, 5-point summary. Independent factorial designs are fully between step designs with more than one IV. And each IV presents a main effect. The combined IVs are investigated as an interaction. Interactions mean the effect of one IV on the DV changes based on the level of another IV. And this is determined by comparing the difference in one IV to the reference category at different levels of the other IV. Factorial models follow the same general linear structure as one-way ANOVAs with just an added term for the interaction effects. Explain variance, variance explained by the model must be separated based on the main effects and the interaction, and then you just calculate an F ratio for each of these sources of variance. And follow up all significant F ratios with plan contrast and our post-hocs or pairwise comparisons, just like what you did with the one-way ANOVA. Okay, so if you are having trouble understanding this, do go back and read your textbook chapter. You can always put questions onto the discussion forum, or you can make an appointment with me during my consultation hours, or email me if you're not available during my consultation hours on Wednesday. Okay, so here's the quiz yourself. So what's an interaction effect? I'll give you a couple seconds before I show you the answer. Correct answer, the effect of one IV on the DV changes as a function of the level of another IV. V0 is an independent factorial ANOVA represents the same thing as V0 in a one-way ANOVA. True or false? Correct answer here is true. Both represent the mean of the reference group, which is coded as 0. What does the coefficient B for an interaction term represent? The correct answer is D, the change in the effect of one IV on the D based on the level of a second IV. This is what an interaction means. Okay, and lastly, what does Sum Squared's model represent? The amount of variance explained by all IVs and their interaction. So this is the total model, full model. Okay, so your turn. All right, now I want you guys to go back to the ANOVA, the concussion example that you guys have been working with. And you have two IVs. Now you guys have already conducted a t-test looking at the effect of age on escape latency, and you did a one-way ANOVA looking at the effect of 0, 1, or 4 concussions. And now I want you to put this together. So conduct a factorial ANOVA with concussion group and age as your IVs and mean latency as the DV. And I'll post the answer key later on. Okay, guys, thank you very much. I'll see you in class next week.